Hello and welcome to Earthly Teachings. In this tutorial, we will be diving into the world of Electrotechnics N4. Today, our focus is on Unit 5.2, which covers single-phase motors. These motors are incredibly common, and you'll find them all around you, from household appliances to power tools. By the end of this lesson, you will be able to describe the characteristics of single-phase motors, explain the operating principle of single-phase induction motors, identify and differentiate between the three main types of split-phase motors, and describe the characteristics and applications of universal motors. So, let's get started with our detailed exploration of single-phase motors. Our first objective is to describe the key characteristics of single-phase motors. To understand these motors better, let's look at their advantages and disadvantages. On the positive side, single-phase motors are very convenient. Single-phase supplies are easily available, making them suitable for residential and small commercial applications. Additionally, they offer easy speed control and their direction of rotation can be changed with relative ease. There are also many different types available to suit various functions, and some can even improve the power factor of a system. However, they do have several drawbacks. Let's look at the disadvantages. A major disadvantage is that many single-phase motors are not self-starting, meaning they require an auxiliary mechanism to begin rotating. Their design can also be complicated, which often leads to higher maintenance requirements and a higher cost compared to simpler motors. They are also relatively larger for the same power output, have limited starting and operating torque, and are generally less efficient than, for example, three-phase motors. So we've now met our first objective. We have a clear understanding of the advantages like easy speed control and the disadvantages like not being self-starting, which sets the stage for our next topic. Our next goal is to explain the construction and operation of a single-phase induction motor, also known as a split-phase motor. We'll begin with the core principle. Unlike three-phase induction motors, a standard single-phase induction motor is not self-starting. Let's understand why. The fundamental problem is that a single-phase AC supply, when applied to a stator winding, produces a magnetic field that only pulsates, it doesn't rotate. This pulsating field is not enough to induce a starting torque in the rotor, which is needed to get it moving. Think of it this way. If you apply voltage and then manually give the rotor a push, it will start spinning. The pulsating field can sustain the motion, but it cannot initiate it. The direction it spins depends on which way you pushed it. This brings us to a crucial question. How do we make these motors self-starting? The solution is to convert the single-phase motor into a two-phase motor, at least for the starting period. This trick is the key to making single-phase induction motors practical. By doing this, we create a system that can generate the rotating magnetic field necessary for the motor to start on its own. We've now established the basic operational challenge and the general strategy to overcome it. Now, let's explore how we achieve this two-phase system concept by looking at the waveforms and vector diagrams. Imagine a motor that actually has two sets of windings placed at 90 degrees to each other. This is a hypothetical two-phase motor, but understanding it is key. When a two-phase supply is applied to these windings, it induces electromotive forces, or EMFs. These EMFs are out of phase by 90 degrees. Consequently, the currents produced by these EMFs and the magnetic fluxes produced by these currents will also be 90 degrees out of phase. Let's look at the waveform diagram. We have two sinusoidal fluxes, phi1 and phi2. Notice that phi1 reaches its peak at 90 degrees, while phi2 reaches its peak at 180 degrees. Phi1 leads phi2 by 90 degrees. Visually, this 90-degree phase difference is also captured in the vector diagram. We represent the peak value of flux 1 as a horizontal vector, phi1. Flux 2 is represented by a vertical vector, phi2. The legend confirms that phi1 is the flux from the first winding and phi2 is from the second. The right angle symbol clearly shows they are 90 degrees apart. This phase difference of 90 degrees is the secret. It allows the two fluxes to combine and produce a single magnetic field that doesn't just pulsate but actually rotates around the stator. This rotating field is what will drive the rotor. Now, let's bring the waveform and vector diagrams together. We'll construct vector diagrams for specific points in time to see how the rotating magnetic field is generated. Our objective here is to visualize the resultant flux, phi r, at 4 key points: 0 degrees, a point between 0 and 90, 90 degrees, and a point between 90 and 180. Let's start with point 1 at 0 degrees. Looking at the waveform, at this instant phi 1 is 0 and phi 2 is at its maximum negative value. This means the flux produced by the first winding is 0, and the flux from the second winding is at its strongest in a negative direction. The vector diagram shows this. There is no vector for phi 1. We only have the vector phi 2 pointing downwards. The resultant flux, phi r, is simply equal to phi 2 pointing downwards. Next is point 2, at some angle alpha between 0 and 90 degrees. At this point, both phi 1 and phi 2 are positive, but phi 2 is still negative relative to its peak. In the diagram, we show phi 1 pointing right and phi a2 pointing downwards. The resultant flux, phi r, is the vector sum of phi 1 and phi 2. At point 3, we are at 90 degrees. Here, the waveform shows phi 1 is at its maximum positive value, and phi 2 is back to 0. So, phi 1 is at its strongest, pointing to the right, and phi 2 is 0. As expected, the vector diagram for point 3 shows only a vector for phi 1, pointing to the right. The resultant flux, phi r, is now equal to phi 1. Finally, let's look at point 4, at some angle beta between 90 and 180 degrees. Now both phi 1 and phi 2 are positive. The diagram shows vectors for phi 1 pointing right and phi 2 pointing up. The resultant flux, phi r, is the vector sum of phi 1 and phi i2. If you follow the direction of phi r in these 4 diagrams, it starts pointing down, then moves towards the right and up, and continues to rotate. This confirms that a two-phase system does indeed produce a rotating magnetic field. This is the principle that allows us to make single-phase induction motors self-starting. We've now visualized how a phase-shifted flux creates a rotating field. We've established that a two-phase system can create a rotating magnetic field, which solves the non-starting problem. Now let's see how we convert a single-phase motor into a two-phase motor for starting purposes. The method is to use 2 stator windings displaced at 90 electrical degrees to each other, just like our hypothetical two-phase motor. We'll call them the main winding and the auxiliary, or starting, winding. Let's first look at the stator construction. Figure 5.17a shows a cutaway of a single-phase motor stator. You can see the windings that are embedded in the slots. There's also a capacitor visible on top, which is connected in series with the auxiliary winding. This capacitor will be essential for creating the phase shift we need. A simplified circuit diagram in Figure 5.17b makes the electrical connections very clear. We have a single-phase supply V connected across terminals L and N. The total current, I, splits into 2 parallel paths. One path is the main winding, which carries current IM. The other path is the auxiliary winding, which carries current IA. Notice that the 2 windings are shown electrically perpendicular. It's important to differentiate between the 2 windings. The main winding is designed for continuous operation. It's made of thick wire and many turns, giving it low resistance and high inductance. The auxiliary winding is only for starting. It's made of thin wire with fewer turns, resulting in high resistance and low inductance. Together, they create the necessary phase-shifted magnetic fields. By adding this auxiliary winding and designing it specifically to have different electrical properties, we can create 2 currents that are out of phase. This phase difference produces the rotating magnetic field, making the motor self-starting. Now that we understand the basic principle, let's look at the first and most fundamental type of split-phase motor, the resistance start induction run motor. Our objective is to explain how this motor achieves a phase shift between the main and auxiliary winding currents to generate a starting torque. Figure 5.8a shows the circuit diagram. It's essentially what we just discussed, but now the auxiliary winding has a centrifugal switch connected in series. The main winding and auxiliary winding are in parallel across the supply. The whole trick of this motor is in the design of the windings, which creates the phase shift. As the name suggests, the auxiliary winding has much higher resistance and lower inductance compared to the main winding. Remember, for a purely inductive circuit, current lags voltage by 90 degrees. For a purely resistive circuit, current is in phase with voltage. Our windings are not pure, but they are predominantly inductive for the main winding and predominantly resistive for the auxiliary. Let's see this on a vector diagram, figure 5.8b. We'll use the supply voltage V as our reference, placed horizontally. Because the main winding has high inductance, the current through it, IAM, lags the voltage by a large angle. Because the auxiliary winding has high resistance, the current through it, IA, lags the voltage by a smaller angle. The crucial point is that IA and IM are now separated by a significant angle, which we call alpha. This phase displacement, angle alpha, is what generates the rotating magnetic field and, consequently, the starting torque. The greater the angle alpha, the greater the starting torque, because torque is proportional to the sine of this angle. If alpha were 0, there would be no torque, and the motor wouldn't start. Now, what about that centrifugal switch? It's connected in series with the auxiliary winding. Its job is to disconnect the starting winding from the circuit once the motor has reached about 80% of its full load speed. It does this by sensing the speed through centrifugal force. This prevents the auxiliary winding from overheating, as it's not designed for continuous operation. This type of motor is relatively cheap and is used for low torque applications like fans, fridges, and washing machines. We have now seen how a resistance start motor creates the necessary phase shift. Demonstration of some lattice output with colors and a board computation. First, we subtract 4 from both sides. This simplifies to x squared equals 16. Let's take the square root on both sides, and so x equals plus or minus 4. Our third and final type of split-phase motor is designed for applications demanding the highest possible starting and operating torque. The capacitor start, capacitor run motor. Our objective is to see how using 2 capacitors allows this motor to achieve superior performance for both starting and continuous operation. The design of this motor, as shown in the circuit diagram in figure 520, introduces 2 capacitors. We have a start capacitor and a run capacitor. The start capacitor is in series with the auxiliary winding and the centrifugal switch, just like in the previous type. The run capacitor is connected in parallel with this combination and stays connected all the time. The operation proceeds in 2 stages. First, during starting, the centrifugal switch is closed. This connects both the start capacitor and the run capacitor in parallel with each other, and this combined capacitance is in series with the auxiliary winding. The total capacitance is therefore the sum of the 2, giving a very large capacitance. This creates an extremely large phase angle alpha, producing an exceptionally high starting torque. Second, once the motor reaches about 80% of its full speed, the centrifugal switch opens, disconnecting the auxiliary winding and the start capacitor. However, the run capacitor remains connected in series with the auxiliary winding for the entire duration the motor is running. This run capacitor improves the motor's power factor, efficiency, and provides better operating conditions. This clever design offers significant advantages: an increased starting torque of over 300% of the full load torque, improved power factor, enhanced efficiency, and overall better running conditions. Consequently, these motors are used in heavy-duty applications like air conditioners, refrigerators, and compressors, where both high starting and running torques are essential. We have now seen how 2 capacitors enable the highest performance. A common requirement for many motors is to be able to reverse their direction of rotation. Let's see how this is achieved for single-phase induction motors. Our objective is to understand the simple principle behind reversing a split-phase motor. The key principle is that the direction of the rotating magnetic field, which determines the motor's direction of rotation, depends on the relative phase of the currents in the main and auxiliary windings. To reverse this rotating field, we simply need to reverse the direction of the current, or polarity, in either the main winding or the auxiliary winding, but not both at the same time. Let's repeat that for clarity. You change the polarity across one of the windings, but not the other. You can reverse the connections to the main winding, or you can reverse the connections to the auxiliary winding. But if you reverse both, the direction of the rotating field will not change. By doing this, the phase relationship between the 2 windings is reversed, which in turn reverses the direction of the rotating magnetic field, and thus the motor will spin in the opposite direction. So a simple wiring change is all it takes. This is a very practical and useful feature for many applications. Now, let's turn our attention to the second major type of single-phase motor we'll consider: the universal motor. Our objectives are to understand its unique ability to run on both AC and DC, describe its characteristics, and list its key applications. The defining feature of a universal motor is its ability to operate on either a direct current, DC, or an alternating current, AC supply. Because its construction and operating characteristics are very similar to a DC series motor, it is also often referred to as an AC series motor. Let's quickly see why it works on both. In a DC series motor, if current is reversed, both armature and field polarity reverse, maintaining torque direction. In an AC supply, the current in both armature and field reverses synchronously, maintaining torque direction. Now let's look at its key characteristics. First, it has a very high starting and operating torque, making it suitable for applications where a strong initial push is needed. Second, it has a variable speed that is highly dependent on the load. And third, it has dangerously high no-load speeds. This is a critical point. Universal motors should never be operated without a load, as they can spin so fast they destroy themselves. The main difference from a DC series motor is that the iron parts of a universal motor are laminated. This is done to reduce eddy current losses that would occur when operating on an AC supply. You can see the exploded construction of a universal motor in the figure below. You'll recognize the stator windings, the rotor with its commutator segments, and the carbon brushes that make contact. Another figure shows the circuit diagram, confirming that the field windings are connected in series with the armature, and it can be connected to either an AC or a DC supply. Applications for universal motors are everywhere you need high torque in a compact package. Think of portable drills and grinders, sewing machines, vacuum cleaners, and food blenders. Because they can operate on standard AC mains and provide excellent performance, they are indispensable for these kinds of tools and appliances. We have now covered the construction, operation, characteristics, and applications of the universal motor. Finally, let's briefly touch on speed control and reversing the direction of rotation for universal motors. Our objective is to see how these two control functions are achieved in a universal motor. Speed control is relatively straightforward. It is easily achieved by including a variable resistor in series with the motor. By increasing this resistance, you reduce the current flowing through the armature circuit, which in turn reduces the speed of the motor. This is a common feature in tools like variable speed drills. As for reversing the direction of rotation, the principle is similar to the split-phase motor. We need to reverse the relationship between the magnetic fields of the stator and the armature. This is done by simply changing the polarity across either the armature or the field coils, but not both. In practice, this is achieved by interchanging the connections to the brush holders, which effectively reverses the armature current relative to the field current. Once again, the rule is to change the polarity of only one part, either the armature or the field winding, to achieve direction reversal. We have now completed our look at universal motors. You can see they are highly controllable and versatile, perfect for the demanding applications they serve. Let's summarize what we've covered today. We started by exploring the general advantages and disadvantages of single-phase motors, noting their convenience, but also their self-starting problem. We then dove into single-phase induction motors, seeing how the non-starting issue is overcome by using a split-phase design that creates a rotating magnetic field. We studied the three main types: the resistance start, induction run, the capacitor start, induction run, and the capacitor start, capacitor run, and compared their starting torques and applications. We also learned how to reverse their direction of rotation. Finally, we examined the universal motor, a remarkable motor that runs on both AC and DC, possesses high starting torque and variable speed, but must always be operated under load. Understanding these different types of single-phase motors is crucial for selecting the right motor for the right job and for success in your N4 examinations. Thank you for watching Earthly Teachings. Subscribe for more Electrotechnics N4 tutorials and revision lessons. We hope this video has been helpful in your studies.